So, welcome to this new lecture on statics ME106, and today we will going to start chapter number 9, which is about the center of gravity, centroid, and center of mass. And so you see, uh, it becomes important for a mechanical engineer to be familiar with the center of gravity of his design, because it plays a very vital role in defining the stability of the objects, stability of your design. For example, as you can see here in these figures, uh, that this ship is basically not able to float, and it has actually uh, toppled over. Okay, and this is because it was not able to achieve the stability. And why this happens? Because uh, the center of buoyancy of this ship was actually below its center of gravity, so it was not taken care during its loading of the cargo, and its center of gravity raises such that the center of buoyancy goes below the center of gravity, and which causes a unbalanced moment to act on this ship, and therefore it loses its stability. So from this figure you can realize that how important it is for an engineer to realize the importance of center of gravity, and how important it becomes to locate or pinpoint uh, the value of center of gravity in your design or in your object. So similarly, if you see here in this figure, during the aircraft and during its flight, in order to maintain the stability of the flight, uh, there are various sorts of surfaces, aerodynamic surfaces installed in the plane. For example, the ailerons, the rudder, the flaps, and they all basically try to exert moment about the center of gravity of the aircraft, and these moments actually maintains the stability of the flight. So it is again important to know the location of the center of gravity of an aircraft. Similarly, while designing this double decker bus, okay, you cannot actually load extra passengers uh, in its top compartment, uh, because the center of gravity can raise, and the bus can become unstable because its center of gravity will going to raise. So it can basically turn over during the turns, sharp turns. Similarly, this racing car shown here, it is basically made flat. Sorry, yes, made very low and wide, and this is because to decrease the center of gravity, to keep the center of gravity as close as possible to the ground, so that when these racing cars are traveling at very high speeds, they and they make some very sharp turns during very high during their speeds, they maintain their stability. So all these figures are actually highlighting the point that in order to study the stability of structures in equilibrium, uh, and in order to design them from safety point of view, uh, the location of the center of gravity will be very important for us, and this is basically the core of this chapter. That is why it is important for us to sort out methods and learn techniques through which we can locate the center of gravity of our design. And this next slide also represents the application of center of gravity in sports physics. For example, this weightlifter you know has basically lowers himself. He has basically lowers himself and increases the base area between his feet. He has increased the base area, which basically lowers the center of gravity, and so it makes this weightlifter stable while lifting this load. So this is an application of center of gravity. How sportsman utilizes the center of gravity for their advantage. Similarly, this sprinter here has assumed a position that basically aligns the center of gravity, his center of gravity, with his rib cage. This will going to help him in attaining high speed when he basically kicks off from his point. And this swimmer has basically assumed a position that basically pushes the center of gravity out from his body, slightly out from his body, which will going to help him dive into the pool at a faster rate. So center of gravity is also being utilized in sports physics. It is utilized in the design of engineering structures, as we see in this first slide, and it is also utilized in learning sports physics. So here basically you can say that the knowledge of locating the center of gravity will really help us in studying the dynamics of rigid bodies. It will going to help us in study dynamics of rigid bodies because it will going to help us in calculating the moment of inertia. And so moment of inertia is basically the property of the structure by virtue of its distribution of mass and its geometry that actually helps the body in resisting angular accelerations. So this is the property moment of inertia, which actually helps in resisting the angular accelerations of bodies under dynamic conditions. And in order to calculate this property moment of inertia, it will be required for us to pinpoint or locate the center of gravity of the object first. So the knowledge of center of gravity can also be used in the design of structural members, because you can use this knowledge in calculating the moment of area. So the moment of area is a property of a structure by virtue of which it resists bending. Okay, so for example, if this is a some kind of a structure that is supported here at this end, fixed support, and you apply a load here, you apply some kind of a load here. So this load will going to exert a moment about this point. This is the moment arm. Okay, so this load will going to exert a moment about this point O, and this moment will basically bend this object. We're going to have an ability to bend this object. Okay, so this will going to create bending stresses in the body. And so the moment of area, the moment of area is basically a property by virtue of which this structure will going to resist bending. So if you are able to locate the center of gravity under a uniform gravitational field, and and your structure is made up of a homogeneous material, then it also coincides with the geometric center of the body, centroid of the body, and that will be very helpful in finding out the moment of areas. So these are two major applications. Rigid body dynamics, where you use the value of center of gravity to find out the moment of inertia, which is the resistance to angular acceleration of a body by virtue of its mass distribution and geometry. And secondly, you can use this knowledge to calculate the moment of areas, which is the resistance to bending offered by a structure by virtue of its cross sectional area. And apart from these, you can also use the knowledge of center of gravity in orbital mechanics, aircraft safety, biomechanics, and learning astronomy. So we will going to we will try to generate some equations that will going to give us idea about how to calculate the center of gravity, center of mass, and centroid of any given volume or area. So here we have some kind of an arbitrary body, okay, and we know that each and every body is made up of particles, so each particle will have a differential weight dw. This differential weight dw is the weight of the particle, single particle, uh, that makes this body, okay, and we know that there are infinite number of these particles in this body. So this is a force actually of the weight acting downward of this particle, and there are number of particles distributed here in this body. So if you sum all of these weights, okay, you will end up with the value of the weight of the body itself, and that weight of the body will going to pass from the center of gravity of the body. Now this is an arbitrary shaped body, so this weight w will going to pass from the center of gravity of this body, but this body is made up of tiny particles. Each particle has a weight of dw acting in the downward direction, z direction. This weight is also acting in the z direction. So we can simply write that by summing the forces in the z direction, we can write that this weight w is actually equal to the sum of all these dw's, which are infinite in number. So when they are infinite in number, you can use an integration sign to sum all these dw's, and sum of all these dw's will be equal to w. Okay, so now there is another thing defined in this geometry, in this figure. This dw is passing from the center of gravity of this particle, and the center of gravity of this particle with respect to this coordinate system, Cartesian coordinate system, is located at z tilde, y tilde, and x tilde. Okay, so a tilde means that you have an x and there is a tilde over it. So you have x tilde, y tilde, and z tilde, which defines the center of gravity of this very tiny particle. And then you have the weight of this entire body, w, which passes from the center of gravity of the body. And this center of gravity of the body is located at x bar, y bar, and z bar. So you can say that x bar is the x coordinate of the center of gravity of this entire body, whereas x tilde is the x coordinate of the center of gravity of this tiny particle. And there are infinite number of these tiny particles distributed in this body. So let's sum the moments about the x-axis. Okay, uh, x-axis, sum the moment about the x-axis of this figure. Okay, this figure number 1, and then we will going to sum the moment about the x-axis on this figure, figure number 2. Okay, so let's start from this figure. Okay, this weight w is basically parallel to z-axis, so this will not going to create any moment about z-axis. This is because of the definition of cross product, because we know that moment is basically cross product of force and momentum, r cross f. So remember that if you have a force defined like this in terms of vector, and you have a momentum defined like this, then r cross f give you the moment of this force, and this moment vector will going to act in the perpendicular direction of the plane containing this r and this f. So this vector, this moment vector, will actually be perpendicular to this plane and perpendicular to this plane. Means this moment vector m will be perpendicular to the plane containing r and f, and this is the plane that contains r and f. So the moment vector will always be perpendicular to the plane that contains the force and its moment arm. So since this force is basically parallel to z axis, okay, uh, and its moment arm is either x bar or y bar, okay. So this force can only produce moment in the y axis or in the x axis, okay, but not in the z axis. So because if the plane of this w is z axis, then its moment arm has a plane that is either x or y. So this can never create moment about the z axis. So you have to remember the simple rule now, that when a force is parallel to any axis, if the force is parallel to any axis, it will never going to create moment about that axis. But this force is very capable of creating moment about the other axis. That is, it will going to create moment about y axis, it will going to create moment about the x axis, but not about the z axis, because it is parallel to z axis. And why it will not going to, why this is true? Because of the cross product, the definition of the cross product. If the force and moment arm shares this plane, then moment can never lie in this plane, it will always be perpendicular to this plane. So if this w shares the direction which is exactly the direction of the z axis, it can never produce moment about z axis, okay. So this is the logical reasoning why this uh, why the force never produces moment about the axis to which it is parallel. So let us sum the moment about the axis. Okay, let us sum the moment about the y-axis. So this is moment about, this equation is representing moment about y-axis. So summation moment about the y-axis in both these figures, 1 and figure 2. So let us take figure number 2 first. This force is parallel to z-axis and its moment arm measured from y-axis is x bar. So you just join the tail. So this is the moment arm, and we join the tail of this w and draw a curl like this towards this w, and we say that this is an anti-clockwise movement, okay. So this x bar into w is the moment of this force about the y-axis, okay. X bar w is the moment of this force w about y-axis. And what is this w? This is the total weight of the body, okay. Then this dw will also going to create moment about y-axis. It will also going to create moment about the y-axis, and its moment arm will be x tilde. So this moment arm is x tilde, and of course you just join the tails, and this moment is also anti-clockwise, and this moment will be equal to dw times x tilde. So it is dw times x tilde, dw times x tilde. But we know that there are infinite numbers of dw's present, okay. There can be a dw here as well, there can be a dw here as well, and so on. So there are infinite numbers of dw's. Therefore, we have used an integration sign. Okay, we have used an integration sign. And similarly, we sum the moment about uh, x-axis now. Using figure 1 and figure 2, we sum the moment about the x-axis. So if you sum the moment of this force W about the x-axis, its moment arm will be y dash. Okay, this is the moment arm y dash from x-axis. So we just uh, join the tails and we say that this is a clockwise moment. So this moment is y dash or y bar into W, y bar into W. And so similarly, this dw will also going to have moment about the x-axis, and its moment arm is y tilde. So again, these two moments will be equal because there are infinite numbers of dw's. So there will be, we will going to use an integration sign. So these two moments will be equal, right? The moment of all the dw's about x-axis will be equal to the moment of resultant w about x-axis, that is y bar w. Similarly, the moment of all the dw's about y-axis will be equal to the moment of resultant w about the y-axis, that is x bar w. Okay. So since this w was parallel to z-axis, we were unable to calculate its moment about z-axis. Okay. So but we need to sum the moment about z-axis as well, because we have summed the moment about y-axis, x-axis, and now we're going to sum the moment about z-axis. So in order to find the moment of this force w about z-axis, we just rotate our coordinate axis. Okay, in this figure number 3 you can see that we have actually rotated our coordinate axis. So x, okay, rotated by 90 degree actually. So we have rotated this coordinate axis by 90 degrees such that z becomes horizontal and x becomes vertical. And now this w is basically vertical, is basically parallel to x-axis. So this w now cannot create moment about x-axis, but it will going to create moment about z-axis. And uh, so we will going to create we will going to have moment about y-axis, because if you will take the moment of this force about z-axis, it will come out to be the same thing, y dash, and we have calculated y bar here. So we need z bar now. So that is why we find the moment of this force w, that is the total weight of this body, about y-axis. Okay. And when we will do so, this distance which is parallel to z-axis will be z bar. So this will appear in the formulation. Therefore, the moment of this resultant weight w about y-axis in figure number 3 is z bar into w, and this will be equal to the moment of all dw's about the y-axis. So we have to use an integration sign. Okay, being consistent with these formulations, z dash or z bar w will be equal to the sum of the moment of all dw's and about the y-axis. So this time taking the moment arm as z tilde. So these three equations actually represents the balance of moment. Okay, these three equations actually represent the balance of moment, as you have noticed. And so we know that this w is nothing but integral of dw. So this w is nothing but integral of dw. So we can replace this w with this integral dw. Okay, on the left hand side of these equations, we can replace w with integral dw. So therefore, the center of gravity, the x coordinate of the center of gravity of this arbitrary shaped body comes out to be integration of x tilde dw divided by integral dw. Similarly, the y coordinate of the center of gravity of this arbitrary shaped body comes out to be integral of y tilde dw upon integral of dw, and z bar comes out to be integral z tilde dw upon integral dw. So these are the uh, equations. These are the equations through which we can find or locate the center of gravity of any arbitrary shaped body. So as you can see that these formulas basically contains integration. So we will be using integration in this chapter to find out these these coordinates. So remember that x bar, y bar, z bar are the coordinates of the center of gravity of the entire body, whereas x tilde, y tilde, z tilde are the coordinates of the center of gravity of the differential element. So this dw was the weight of a very tiny particle. We say that this particle is of differential size, and so this becomes a differential element. And if you sum up all these tiny particles, all these differential elements, you will again come up with this body. So therefore, please remember that the formulations for center of gravity involves integration, and it involves x tilde, y tilde, and z tilde, which are the center of gravity of the differential element. So for center of gravity, we will be using these formulas in future. So what is center of mass? Okay, point at which the entire mass of the body acts, and we note that differentially small element that we considered uh, in the previous slide, okay, which was having a weight dw, which was having a weight of dw, we can use the expression w equals to mg to define the differential mass of this element, of this differential element. So each dw will be equal to g times dm, where dm is the differential mass. So since this differential element has a weight which was equal to dw, it will also going to have a mass which will be equal to dm. And these dm and dw, which are infinite in number, they are related with the gravity constant g, acceleration due to gravity. So because w is equal to mg, so we have just written this equation in form of differential, dw equals to g times dm. So therefore, from the previous equations, if you substitute in place of dw gdm, you will just simply transform the previous equations, which were for center of gravity, to center of mass, formulations for center of mass. And knowing that this g is basically a constant, it will going to cancel out from the numerator and the denominator, leaving behind these expressions. So nothing has changed, just dw has been converted to dm by using this equation. and these equations represents the coordinates of the center of mass of your body. And you have to keep this in mind that the center of mass and center of gravity will always going to coincide with each other if the gravitational field is uniform. So this means that if the gravitational field, when it is uniform, then Cm is nothing but Cg. Center of gravity and center of mass will coincide. They will lie exactly at the same point. So for example, let's say that we have this cylinder, and the lower portion of the cylinder is made up of steel. Okay, and the top portion of the cylinder is made up of aluminum. So we know that steel being heavier than aluminum, the center of gravity of this cylinder will shift towards the steel, and therefore the center of mass will also shift towards steel. So even though this material is non-homogeneous, this structure is non-homogeneous, made up of two different materials, not of single material. But even in this case, the center of mass and center of gravity will going to coincide, because center of mass will shift itself towards the heavier material, and therefore center of gravity will also going to shift towards the heavier material. And so this is true that center of mass and center of gravity will coincide as long as this material is placed in a uniform gravitational field. So this center of mass and center of gravity will only going to be different if g is actually changing, if g is some kind of a function of uh, let's say the height h. So for example, let's say if you are taking this material, this structure in a spaceship, and that spaceship is basically entering into the space, it is leaving the atmosphere uh, of earth, the surface of earth and its atmosphere eventually, and it is entering into the space, then there will be a variation in the gravitational field. In that case, the center of mass and center of gravity will going to be different. So center of mass and center of gravity will only be different if there is if the gravity field is basically of varying nature. Otherwise, they will always going to coincide with each other. Even though if the material is made up of different, the structure is made up of different materials. So we have defined center of gravity and its formulations. We have defined center of mass and its formulations with just a little bit of manipulation of equation. We come to the third important concept, that is of centroid. So centroid of a body is basically the geometric center of the body. Okay, the point about which the volume or area is equally distributed is known as the centroid. So using the equations of center of mass, we can actually formulate uh, the the expressions for centroid. We know that mass is basically equal to density times volume. So since we are talking about the differential element here, which has a differential mass dm, then it will going to have a differential volume dv. So this dv and dm will be related to each other with the material property known as density. Okay, so if we assume that this density is constant, which means that the body is made up of only single material, only one material. Okay, in that case we can substitute in place of this dm, and of course this dm as well, rho dv. And if we assume that the body is made up of single material, then density will remain constant, and it will be cancel out from the numerator and denominator, leaving behind the expressions for centroid of the body. So this, in place of this dm, this dv will going to appear. Okay. So these are the expressions for centroid of your volume. And please remember that that if you are dealing with a area, okay, if you are dealing with the area, not with the volume, okay, that even an area has a centroid. It is the point about which the area is equally distributed, the geometric center of the area. In that case, you can just replace this dv with dA, x and y. So it is not a volume, therefore there is no z bar, z dash. Okay, there is no z dash. So we generated the expressions for center of gravity, and then we converted it into center of mass expressions for center of mass by using this definition dw equals to gdm. And then we converted the expressions of center of mass to centroid by using the expression mass is equal to density times volumes. And simply, if you are dealing with with area, two-dimensional entity, you just replace this dv with dA. Everything will remain the same. So one thing to note, that C coincides with Cm for a single homogeneous material density only. Means if this cylinder is made up of just one single material, then its centroid will lie on the axis of symmetry. This is the centroid C, and this will be the center of mass as well. If this cylinder is made up of one single material, but if this cylinder is made up of, let's say, two different materials, like this, the top portion is aluminum, and the bottom portion is steel, then you see that the centroid will still remain the geometric center of this shape, which is the cylinder. Okay, but the center of mass will going to shift towards the heavier material. So center of mass will going to come here. Yes, maybe here. So this will be the center of mass then. And since the gravitational field is constant, this center of mass is also equal to center of gravity. So center of gravity and center of mass will remain the same. Okay, but centroid will going to change. If this shape, this body is made up of two different materials, or maybe more than two different materials. Okay, so this is why that is why you say that C only coincides with Cm for a single homogeneous material density. Otherwise, the center of mass will shift towards the heavier material. The centroid will going to will still be the geometric center of the body. And you see, uh, if your body has an axis of symmetry, if your body has a very well defined axis of symmetry, then centroid will always lie on that axis of symmetry. For example, this is the cone. Okay, it's a three-dimensional body, and it is a cone. So this cone has a very well defined axis of symmetry, which is this y-axis. Therefore, the centroid of this cone will only lie on the y-axis. It has nothing to do about the z-axis and about the x-axis. It will only lie upon the center, sorry, the axis of symmetry. So if your given area or your given three-dimensional volume body, uh, it has a very well defined axis of symmetry, then centroid will always lie on the axis of symmetry or at the intersection point of axis of symmetry if it has axis of symmetry in two planes. For example, this cylinder, it has an axis of symmetry in two planes, this y-axis and this x-axis. So centroid will always going to lie at the intersection of the axis of symmetry. Okay, if your area or your volume has no axis of symmetry, then you have to use these integration, these formulas. So you can simply have a geometric center of your area or of your volume if it is a uh, if it is some common shape. Like for example, for a sphere you have a centroid at its center. For a circular disk you have centroid at its center. You can very well define the centroid of a triangle. You can very well define the centroid of a rectangle or a square. But if your shape is of some kind of an irregular geometry, then there is no option. You have to use integration to find out the values of its geometric center, center of gravity, center of mass. Okay, and you have to keep this in mind while using these formulas, that the only case in which centroid, center of gravity, and center of mass coincides, okay, is when the body is made up of only one single material and it is placed in a uniform gravitational field. Only in that case, centroid, center of mass, and center of gravity will coincide with each other. I mean that uh, all these things will going to lie at one common point in your body if it is made up of single material and if it is placed in a uniform gravitational field. If it is made up of two different materials or more than two different materials, then its center of mass and center of gravity will not going to coincide with its center of geometry, that is centroid. But centroid will be different, and center of mass and center of gravity will be different. They will going to shift towards the heavier material. And if in case the gravitational field is also not uniform, then center of mass and center of gravity will also shift. They will not going to coincide. Okay, so integration formulas can be used uh, where the shape, area, or volume is not regular. But if the shape and area is very regular, then you can basically convert these integration formulas into summation, and you have a concept of composite bodies or composite shapes. So a composite body, which can be a 3D volume or a 2D areas, is a series of connected simpler shaped bodies. For example, you see here that this structure is made up of uh, three different shapes. You have here a cone, so you have here a cone, and this is a cylinder. This is a cylinder, and this is a hemisphere. So this is a hemisphere. So three different geometries are combined together to form this one structure. This is a composite body made up of three different shapes. But please note that all these three different shapes are simple shapes for which we have well defined formulas available for their centroid, and if they are made up of single material, then centroid, center of mass, and center of gravity remains the same, because in engineering, uh, all the time our structures and designs are basically on the earth, so the gravitation field is uniform, unless you are designing something that needs to go out in the space. In that case, the gravitational field can vary, but mostly the structures are under a uniform gravitational field. So this means that if you can calculate the centroid of this entire body, you have also calculated the center of gravity and center of mass, provided that all these simple shapes are made up of one material. Similarly, this barricade is made up of two different shapes. Okay, this shape resembles a trapezoid. This shape resembles a trapezoid, and this shape resembles a rectangle. So this is a rectangle, and this is a trapezoid. So this body is made up of by combining two shapes together, trapezoid and a rectangle. So this is also a composite body. Now, if you assume that these two materials, these two shapes, trapezoid and rectangle, are made up of one single material, and they are placed in uniform gravitational field, then the centroid will coincide with center of gravity, and it will coincide with center of mass. So there is no difference. You calculate the centroid or the center of gravity or center of mass, all of them will going to coincide together. Similarly, this beam is made up of three different shapes. Sorry, not different shapes, but rectangles only. So this is one rectangle. This is the second rectangle, and this is the third rectangle. So by combining these three rectangles that are simpler shapes, you have made this composite shape. So this is a volume, composite volume. If you look at this, then it can be a composite area. In both the cases, uh, they have they are known as the composite bodies or composite shapes. So you can just replace the integration sign with a sum here. Just replace the integration sign using summation. Integration actually means summation. So integration sign can therefore be changed to summation sign, right? And your formulation becomes x bar summation of is equal to summation of x tilde w divided by summation of w. Similarly, y bar equals to summation of y tilde into w divided by summation of w. Then z bar equals to summation of uh, z tilde w divided by summation of w. And if you want to find the values of centroid, then just replace these w's with a or v. If you are finding the values of centroid, then just replace this w with a if you are finding the centroid of an area, and if you are finding the centroid of the volume, just replace this w with v. So nothing changed, just you have replaced the integration sign with the summation sign for composite bodies. And remember that composite bodies will always going to have simple shapes for which you can have a simple formulas available. So this brings us to the end of chapter number sorry today's lecture, and in the next lecture we will going to solve problems using these formulations that we have developed. So please go through this lecture uh, attentively, thoroughly, and prepare lecture notes. If possible, prepare your questions and refer to your textbook. So until we meet in the next lecture, good luck.